This is Unit 10B, and we'll begin with Taylor polynomials. Polynomial functions can actually be used to approximate functions such as sine of x, e to the x, and the natural log of x. Let's take a look at this. On our calculator, we're going to graph in a Zoom 4 window and compare both of these functions. Okay, so I went ahead and you can pause the video if you like. I went ahead and put both of those functions under the y equal button. So the sine of x is in y1, and x minus x cubed divided by 3 factorial plus x to the 5th divided by 5 factorial. And don't forget that the factorial can be found under math, arrow over to probability, and I believe it's number 4, but you can take a look. Okay, so if I zoom 4, you can see here that the graphs overlay each other between when you get pretty close to, you can see the values right here. In this window, they overlay each other. So when we're very close, you could say to 0, the functions are nearly the same. Now, as you move away from x equal to 0, you can see that they change drastically. But when you're close to 0, they look quite the same. So that is something that I want you to keep in mind as we learn about Taylor polynomials. So polynomial functions are very easy to work with. They're nice, smooth functions, and they help us approximate these other types of functions, okay? So let's go ahead and begin the definition of an nth degree Taylor polynomial. The nth degree Taylor polynomial. If a function has n derivatives at x equal to c, then the polynomial p sub n of x is equal to f of c plus f prime of c multiplied by x minus c plus, and you can see all of the continuing terms. Now x minus c would be x minus that center, and we're going to be talking about c as the center. Okay? So all of them have that term. Now watch this. The function itself, the first derivative, the second derivative, the third derivative, and the nth derivative, okay? So we continue to take the derivative and evaluate it at c. Okay? Now, let's look at this denominator. 0 factorial, 1 factorial, 2 factorial, 3 factorial, n factorial. And that is the nth degree Taylor polynomial for your function at c. And it is named after Brooke Taylor, who was an English mathematician. Now, what if c was 0? What if your center was 0? We call that a Maclaurin polynomial for your function. And of course, that's named after a Scottish mathematician, Colin Maclaurin. So let's just jump right in. Suppose that that f is a function which has continuous derivatives, and they actually give us these function values. F of 2 is 3, f prime of 2 is -4, f double at 2 is 7, f triple derivative at 2 is -5. Write the Taylor polynomial of degree 3 for f centered at 2, okay? So here c is equal to 2. Let's go ahead and do that. A degree 3 would be the third degree polynomial. Now remember, the first term is always going to be the function evaluated at the center. So it's just going to be f of 2. And then we're going to we're going to add f prime of 2 multiplied by x minus 2. And then we're going to add f double prime of 2 multiplied by x minus 2 squared over 2 factorial. And then the last one we need, since it was a third degree Taylor polynomial, triple at 2, the third derivative, x minus 2 cubed over 3 factorial. Let's fill this in with what they gave us. F of 2 was 3. F prime of 2 was negative 4 times x minus 2. F double prime was 7 times x minus 2 squared, all over 2 factorial. And f triple prime of 2 is a negative 5 times x minus 2 cubed over 3 factorial. And that is the third degree polynomial. Okay, let's try the next one. Find the Taylor polynomial of degree n equal 4. So we need a fourth degree Taylor polynomial. And here is our function. And we would like that centered at 2. So this time, they don't give us the function values. We have to find them. So let's go ahead and find them. Let's find our derivatives first. Our function is e to the 3x. F prime of x is 3e to the 3x. F double is 9e to the 3x. Third derivative, 27e to the 3x. And we have to go to the fourth derivative because we wanted a fourth degree polynomial. And that would be 81e to the 3x. Now, we need all of these evaluated at the center, at 2. So f of 2 is e to the 6th. F prime of 2 is 3e to the 6th. F double of 2 is going to be 9e to the 6th. Third derivative at 2 is 27e to the 6th. And that fourth derivative evaluated at 2 is 81e to the 6th. So we had to find these this time. They were not given, okay, like they were in the previous example. So now I think we're ready to go. Let's go ahead and write the fourth degree Taylor polynomial is going to be, let's just go ahead and write it, f of 2 plus f prime of 2 multiplied by x minus 2 all over 1 factorial, of course, plus f double prime, which is 9e to the 6th, x minus 2 squared, all over 2 factorial. And you could go ahead and include 1 factorial here and 0 factorial if you'd like, plus 27e to the 6th, x minus 2 cubed, over 3 factorial, and one more, plus 81e to the 6th, x minus 2 to the 4th power, all over 4 factorial. And usually we don't simplify those. We usually just leave that there. If you are using a TI-89, there's some notes for you. Okay, let's move on to Maclaurin. When you see Maclaurin, you know your center is 0. Okay, and we're going to talk more about these centers of these series. Okay, so right now, just make note of that. What do you notice? We are not given any of these function values or derivative values, so we need to go ahead and find them. So we have f of x equals the sine of x, and f of 0 is 0. The sine of 0 is 0. The first derivative is the cosine of x, and f prime of 0 is 1. And we need a degree 5. So we will go all the way to the fifth derivative, okay? f double prime of x is the negative sine of x, and of course, you're back at 0. Third derivative, negative cosine of x. Third derivative at 0 is a negative 1. Fourth derivative is the sine of x, and we see a little cycling here, and we're back at 0. And one more, the fifth derivative is the cosine of x, and the fifth derivative at 0 is going to be 1. Okay? So let's go ahead and see what we have. So the fifth degree polynomial is going to be equal to, so what do you notice? That first f of 0 is what we put there, and we could actually go ahead and write this out. This would be f at the center plus the first derivative at the center multiplied by x minus 0 all over 1 factorial plus f double prime of 0 times x minus 0 squared over 2 factorial plus the third derivative x minus 0 cubed over 3 factorial plus fourth derivative x minus 0 to the fourth over 4 factorial plus the fifth derivative x minus 0 to the fifth over 5 factorial. What did you notice here? If you can see that we really could have just written x and x squared and so forth, okay? But I just really wanted you to see this. So let's go ahead and write this. F of 0 is 0 plus 1 times x plus 0 times x squared. Plus a negative 1, let's go ahead and write that as a minus, minus 1 times x cubed plus 0 times x to the fourth, and then plus 1 times x to the fifth. Now I did forget here, just writing those numerators out. This is 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial. So what do we have? Take a look. We lose this 0, and we end up with just x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. So it's kind of a neat thing because it simplifies beautifully, and that's what we get. And there is your Maclaurin series degree 5 for f of x equals the sine of x. Okay, let's go to B. They want us to give them f of 1.4. So basically we're going to use what we have here, p of 5, as the approximation. So it's about equal to the fifth degree polynomial evaluated at 1.4. So we could go ahead and put that in our calculator. And we would have 1.4 minus 1.4 cubed divided by 3 factorial, which is 6, plus 1.4 to the 5th power divided by, and we can do 5 factorial here, 5 math 4. Okay, and you should get 0.987485. Okay, so we get about equal to 987.485. Now, what's interesting about this? Let me show you here. What we're saying is that using that approximation, f of 1.4 is about equal to that. Now, since f of x is equal to the sine of x, f of 1.4 is actually equal to the sine of 1.4. And if you put that in your calculator, you'll get 0.98545. So look how closely approximates the sine of 1.4. We can put that here, sine of 1.4. I hope I'm in radians, which I think I am. Okay? So a close approximation. Let me just change that. So what did we do? We used a 3rd degree Maclaurin polynomial, 5th degree, to approximate the sine of x. Okay, so what is the error of our approximation? This is what it's going to look like. That's what our error looks like. So this is actually equal to 0.98545 minus 0.987485. And if you put those in absolute values, you'll get about 0.002035. Okay? Now they ask us to find the value of f of 2.1. The first thing we're going to do is f of 2.1 is about equal to the 5th degree polynomial at 2.1, and I'll just give you these values so that we can keep going, and you can pause the video and put these in your calculator. And I got 0.0020, and I got 0.89684. And then when I actually found f of 2.1, which is equal to the sine of 2.1, I got 0.863209. Now that error, if you would subtract those, did I put absolute values last time? Yes. The actual value minus our approximated value, and I got that to be 0.03463. How does the error for the 5th degree evaluated at 2.1 compare to the error for the 5th degree compared at 1.4? So what you should notice here is that the error is greater. When x equals 2.1. What do you think would happen if we used our polynomial to estimate the sine of 2.7? The error would be even greater. So I want you to think about those graphs that overlaid each other when we first started. And I don't know if I drew them correctly, but when we are closer in here in this area and we are using our graphs to approximate, the error is small. But as we move away from this center, here the error grows. Okay? So that is of significance as we move forward. Here are some more TI-89 notes if that's what you are using. So to use Taylor polynomials effectively, we need a way to estimate the size of the error, and this is provided by Taylor's theorem. And it goes like this. If a function f is differentiable through order n plus 1 in an interval containing c, then for each x in the interval, there exists some number z between x and c such that this occurs. So what's important right here? This error right here, okay? And so actually what that is going to be the next term, the next derivative, okay? And we're going to talk more about that. One of the useful consequences of Taylor's theorem is that this remainder is less than this term here. We're going to talk more about this max term. Basically, it's the maximum, the absolute value of the maximum of this function value evaluated at z. And z is somewhere between, that value is somewhere between x and c. Basically, it gives us a bound for the error. It does not give us the exact value, and this is called Lagrange's form of the remainder, or you could call it the Lagrange error bound. So we are going to be studying this at length later, but I just wanted you to see these. And this is definitely all one term right here, okay? So let's go ahead and just take a peek at this. Given P2 of x, so that's a polynomial approximation. It's a second degree Taylor polynomial for f about x equal to 0. So that's our center. What are the signs of A, B, and C if f has the graph pictured on the right? Well, let's go ahead and write that second degree Taylor polynomial. That's a plus bx plus cx squared. Now, a is going to equal f of 0, okay? Right here. I could even move that right here. A is going to equal f of 0. That's your y-intercept. Okay? And B is actually going to equal f prime of 0, which is positive since f is increasing. So I'm really running out of room here. Let me see if I can move all of this down. Okay. And then what about C? We notice that this graph F is increasing and F is concave down. Okay. So if F is increasing, F prime of X is positive. And f double prime of x has to be negative, okay? Since we're concave down, increasing, okay? So that's what we have here. C is equal to f double prime of 0, which is going to be negative since concave down, okay? So that's what I wanted to write that out. So therefore, A, look at this, the y-intercept which is equal to A is positive because it's above the x-axis. So A is positive, B is positive, and C is negative, okay? Okay, so that worked out really nicely. Let's go on to the next example. Suppose that the function f of x is approximated near x equal to 4 by a third degree Taylor polynomial. And there it is, right here. There's our third degree Taylor polynomial. Okay. So find the value of, move that up just a touch. Find the value of f of 4, f prime of 4, f double, and f triple. Now keep in mind that these are the, right here, this P3 of x. Let's just go ahead and write it out. Keep in mind that f of 4 goes here. I was wanting to change colors here. This is f of 4. And I don't see an x, let's go ahead and write that down. F of 4 is equal to 2. F prime of 4 is 0. Since, what do you notice? The x minus 4 term is missing. There is no term that shows that, okay, right here. I could do it with this pencil right here. Right in there would be the x minus 4 to the first power, okay? So then what do we notice? We notice that f double prime of 4 divided by 2 factorial has to be equal to negative 5. So this negative 5 right here is f double prime of 4 divided by 2 factorial. So what could you say? You could say f double prime of 4 is equal to negative 10. Okay, and then let's go ahead and look at f triple. So the third derivative of 4 divided by 3 factorial has to be equal to 8 right here in front of this x minus 4 to the third. So the third derivative of 4 is equal to 8 times 3 factorial. 3 factorial is 6. So 8 times 6 is 48. Okay. Does f have a local maximum, a local minimum, or neither at x equal to 4? So we want to know local max, min, or neither, and we need to justify. Well, since f prime of 4 is equal to 0 and f double prime of 4 is less than 0, what happens? So that means that we are concave down here, and f prime of 4 equal to 0, it looks like this. This is actually the second derivative test. So f has a local, what do we have here? A local max at x equal to 4. Okay? The function f has derivatives of all orders for all real numbers x. And here, if you notice, they are giving us all of the function and derivative values evaluated at 3. So you know that that center, you know that that center is going to be equal to 3. Write the third degree Taylor polynomial for f about x equal to 3. So, you know, you could either write P3 of x or you can write T3 of x. Either way. I'm going to go ahead and use T3 of x this time. So T3 of x is equal to, remember your first one is f of 3, so that would be negative 4. And then now we're going to use the first derivative multiplied by x minus the center. Then we're going to get that second derivative evaluated at 3, x minus 3 squared over 2 factorial. And then the last one, and that's a negative 5. So it would be minus 5 times x minus 3 cubed over 3 factorial. It's as simple as that. Right. Okay, let's look at example B. Write the fourth degree Taylor polynomial for g of x equals f of x squared plus 3. Well, in the previous problem, in part A, we had a Taylor polynomial. So we had T3 of x for f of x. So now we want f of x squared plus 3. So our previous x is now x squared plus 3. Let's see what we have. Our fourth degree Taylor polynomial, you may not see it yet, but our fourth degree Taylor polynomial is actually going to be negative 4 plus 2 times. Now our x is going to be x squared plus 3, and we still need that minus 3 that's there, plus 7 times x squared plus 3. We still have that minus 3 all squared over 2 factorial. Now we don't need this next term. Since this is fourth degree, we will have an x squared squared, okay? So those cancel, and we end up with a negative 4 plus 2x squared minus 7x to the fourth over 2 factorial. Now what do you notice? Note that this is negative 4 plus 2 times x minus 0 squared minus 7 times x minus 0 to the fourth over 2 factorial. So we did have a center of 0. So this is our fourth degree Taylor polynomial for g of x. And that concludes this first part of Unit 10b.